The final type of octet rule violation is those atoms that have expanded valences. So we've looked at unfilled valences and radicals. Now we want to move on to molecules with more than 8 electrons around a single atom. For example, SF4. So we definitely know this molecule exists, and this is our Lewis structure to represent what the bonding in this molecule is. And so if we look, it has 4 single bonds on the sulfur, 1, 2, 3, 4, and it has a lone pair. So that would be a total of 10 electrons. That's violating the octet rule. There are more than 8 electrons. So once we start to get into these expanded valence molecules, where atoms have more than 8 electrons, how we can understand and predict which Lewis structure is the best is which Lewis structure gives us formal charges of 0. With expanded valence, we have to throw the octet rule out. We can't really use it. Formal charge is going to be key. If sulfur is going to form a bond with 4 different fluorine atoms, which we know it does, the Lewis structure where it forms 4 single bonds and has 1 lone pair is going to be the most stable or the preferred one because that gives us a formal charge of 0 on every single atom in this molecule. When we are going to use expanded valence in a Lewis structure, the atom needs to have an atomic number of 13 or higher. Smaller atoms, like say fluorine that has atomic number 9, cannot have an expanded valence. The reason for this is we know as the atomic number gets larger, we're moving down the periodic table, atoms get larger. The atoms just need to be big enough to fit that many bonds. There are so many more bonds and lone pairs on this sulfur that it needs to have the size in order to accommodate that. So looking at our periodic table, we can draw a line that basically aluminum, is right here at number 13. Everything below this line is can do expanded valence. Everything above this line can't. And so you'd think, why do we really care? I mean, that seems like, why do we use the octet rule? That most atoms can have expanded valence. But you'll note things that are up above it, carbon, nitrogen, oxygen, fluorine, those are some of our primary, kind of atoms that make up a lot of the most important molecules, especially in living things. The other thing to note is just because an atom can have an expanded valence doesn't mean it always has to have that. There are plenty of molecules where sulfur, phosphorus don't form expanded valences, where they follow the octet rule, and under certain circumstances, you can generate, this sort of kind of expanded valence setup. The reason why, again, has to do with size. Atomic size decreases down a column, and the reason why it decreases is because the orbitals get bigger. We haven't really talked about orbitals since we moved into Lewis theory, but underlying this is still the same quantum mechanics. 3p orbitals start to matter, or start to be the valence for things like silicon, phosphorus, sulfur, whereas when it's carbon, nitrogen, oxygen, those are 2p. Those are smaller orbitals. They cannot accommodate the number of bonds that would need to be formed. And so that doesn't work. And so that's why they can't have an expanded valence. And so, not expanding your valence generally is preferred, but if push comes to shove, phosphorus and sulfur can do it because they're bigger. And the reason why expanded valence comes about is because it offers more bonding. Basically, it is driven by the need to bond more atoms into the molecules. And so if we look at these things like SF4, PCl5, and ClF3, one of the things important to note, all of them are in period 3, all those central atoms, right? Sulfur, phosphorus, and chlorine are all in the period 3 where they have they're big enough. Their atomic number is large enough, they can undergo this sort of expanded valence. But importantly, every single time, these structures, the central atom still has a formal charge of 0. You can see that for sulfur over here, we already talked about that, the 4 bonds and the 1 lone pair. Phosphorus over here with the 5 bonds, it now has 10 atoms in its valence, 5 single bonds. And that's okay because it has 5. If we calculate the formal charge, we know as an atomic valence, it's just an atom off the periodic table, we have 5 minus 1/2 times 10, that gives us a formal charge of 0. Chlorine, 7 minus the 4 from the 2 lone pairs. And then we have 1 or 2, 4, 6 from the bonds. And perfectly fine. We again have a formal charge of 0 with that distribution. If we kind of take a look going back to the sort of atomic pairing perspective, if we look at the Lewis structures of the Lewis symbols for the atom, sulfur, we would say it has 6 valence electrons, 2 are paired, 2 are unpaired, and then 4 are in lone pairs. Each of the fluorines has 1 unpaired electron. And so normally when we go about forming bonds, we would say that those would pair up. And so traditionally we would expect sulfur would tend to form 2 bonds. And if you just have, say, plenty of sulfur, plenty of fluorine, and they can form molecules, this is what you're going to end up with. But say you introduce a lot of extra fluorine atoms, right? There's just a ton of fluorine present. Those fluorine atoms are reactive and they want to start getting into these molecules. Sulfur has more electrons that it theoretically can share. And so what happens is one of those lone pairs that's on the sulfur basically gets shared. Each of those electrons goes and gets shared. So one of the things you'll note, sulfur tends to form 2 bonds when it just shares its standard unpaired electrons. If you're going to expand the valence, you expand by 2. So sulfur could have 2 bonds, or it could have 4. You would not expect it to have 3 bonds because it needs to be sharing all of the electrons that it's starting with. Basically, each one of them, they started out, sulfur was like, I don't need to share this, it's a lone pair, but hey, there's all these fluorines that are really grabby. Now you can start to break that up and share with those. And that's how you can drive this additional bonding. The motivation to expand the octet of the sulfur is driven by the presence of additional fluorine atoms that want to bond. Because sulfur is bigger, it can accommodate them. But again, we have true sharing. When the formal charge is not 0, that corresponds to ideas like donations of electrons. But here, the sulfur had these electrons, the fluorine just is forcing it to share them. But that's fine because it's still just the sulfur is putting 1 electron into those shared pairs. So formal charge is 0. No donation, nothing like that. If we go to phosphorus, we normally think it has 3 unpaired electrons, so we would expect it to form 3 bonds. And again, PCl3 is a stable molecule. PCl3 is about as, kind of what we'd expect if you react phosphorus and chlorine. But again, if you get a lot of chlorine in there, way more chlorine, those chlorines can start to react with the PCl3 molecule. And again, you would take 2 of them where each of the chlorines will get one of the paired electrons that was on the phosphorus. You break up that pair of electrons that's on the phosphorus, and each of them goes into forming a new bond. So you can have 3 bonds on phosphorus or 5, but you can't have 4 because you got to go up by 2.